Next, we will introduce the topic of polar coordinates. So first, let's discuss what are the coordinate systems in general. So what is a purpose of having a coordinate system or even multiple systems? Well, one purpose that coordinate systems serve is we should be able to, for any point in space, assign a set of numbers called coordinates, pass these coordinates to someone else, and the someone else has to be able to use these coordinates to find the exact point in space. So one coordinate system that we are all familiar with that does exactly this is called the rectangular coordinate system, or it is also called the Cartesian coordinate system, and it is named after the French mathematician Descartes. Not sure how to spell his name, maybe like this. And the way it works is we have two axes. We're talking about the two-dimensional coordinate systems here. One, the horizontal, is called the x-axis. The vertical one is called the y-axis. Where they intersect is called the origin. And from the origin, we have positive direction. It has to be indicated somehow for each axis. I indicated by an arrow, so arrow shows the positive direction, and each axis will have its own scale. The scale doesn't have to be the same, so 1 unit on the x-axis may be 10 units on the y-axis, so each axis has its own scale. And then for every point in two-dimensional space, we assign two coordinates according to this rule. So we drop the projection from the point to x and y axis, and wherever they intersect, those projections, the x and y axis, where it intersects the x axis, is we call the x coordinate. So this first number, we usually write it first. That's just a matter of convention. We could have agreed to write the y coordinate first. It doesn't matter, so we would have gotten used to it anyway. So we have 2 points, two numbers, which we call the x and y coordinates. Sometimes the x coordinate is called the abscissa, and the y coordinate is called the ordinate, but that's like the old school way. And now, using this set of rules, it becomes pretty clear. We definitely all should know how to perform the following two tasks. So we definitely know how to find the point given the coordinates, and we also know, if the point is given, how to find the coordinates. So these are naturally the two basic skills that we should be able to perform, or the skills that we have that will allow us to perform these tasks. So, for example, if I ask you to identify the point with coordinates for -1, we should be able to do that by drawing the x and y coordinate axis. Again, I'm talking about point for -1, measuring 4 units towards the y along the x-axis, 1 unit down vertically, and this is the point that we say has coordinates for -1. So this is the x coordinate 4, this is the y coordinate -1. So we're really good at rectangular or Cartesian coordinates. However, this is just one coordinate system, and there are many of them. I guess there are many that we can create. but the useful ones, there are not that many. But alternatively, we can consider the different rules that still will allow us to perform the same two tasks. That is, given the coordinates, we should be able to find the point, and given the point, we should be able to assign the point a set of numbers, in this case 2, that we would call coordinates. So how do the polar coordinates work? Well, unlike the Cartesian coordinates, in polar coordinates we only have one axis. It's called the polar axis. And the point where the polar axis begins, it's the analog of 0, but it's called the pole. And on the polar axis, we also have a scale, so we could have 0 is at the pole, and then we can have 1 unit, 2 units, etc. Now we can extend the polar axis in the negative direction and continue labeling the axis with negative values. So it will be -1, -2, and so on. Now, how do we assign coordinates in polar coordinates? Well, let's pick a point, and when you pick a point, again, if you think about it carefully, like how would you give someone the instructions to find this point in space? Well, one way we can say, like, well, move along the x-axis 1.5 units, or looks like 1.5, and then move upwards like another 1.5 units, so whatever it looks like it here, right? So that will be Cartesian. What would be an alternative way? Well, alternatively, we could say, hey, stand at the pole, face the polar axis, then turn counterclockwise until you face the desired point, and then move in that direction this right here distance. So instead of going horizontally then vertically, you can just turn a certain number of certain angle measure, which we can identify as theta, and then move forward along this line, which we call actually ray. It has the beginning and doesn't have an end in one direction, and move along this ray r units. And that's actually enough for us to later be able to find this point in space. So these two numbers we call coordinates. The r is called the radial coordinate, and theta is called the angular coordinate. So just like we have x and y, abscissa and ordinate, I forgot. Here we have radial and angular coordinates, and that's it. So now, in order for us to call it a working coordinate system, we got to make sure that we know how to perform these two tasks. So do we know how to find the point given the coordinates, and do we know how to find the coordinates given the point? So we already talked about how to find the coordinates given the point. Let's practice how to find the point given the coordinates. So let's go ahead and find where would the point 2, pi will be. So to find the point 2, pi using polar coordinates, we have to follow the instructions. So first we're going to start facing the polar axis, then we're going to turn pi radians counterclockwise direction, so that will take us here. So now we're facing the opposite of the polar axis, and we move 2 units. So this point right here is the one that has coordinates 2, pi. All right, let's find the point. How about 1, 7 pi over 4? Where would that point be? Well, first we have to turn 7 pi over 4 units. So 7 pi over 4 will take us all the way into the 4th quadrant. So now we're facing this way, and we're gonna move along this ray 1 unit. So this is the point that will have the coordinates 1, 7 pi over 4. So it seems like we now convinced that this is a working coordinate system. So let's practice a little bit more. Let's go ahead and plot using the polar coordinate system the following points. And to plot, we're gonna have to draw the polar axis, and we're gonna label the pole. We're gonna introduce the scale, and we need to find a way to measure the angle. I'm going to superimpose the picture of this protractor to make it easier for us to measure the angle. So let's find where the point 1 will be. We're going to measure 3 pi over 4, which will take us somewhere in this direction, right? This is 135 degrees, and we're going to measure exactly 1 unit, which will be around here. So this is the point A. Now let's find the point B. Pi over 6, 2, so we're going to measure pi over 6 units, so we're going to be facing this way, and we're going to move along this ray 2 units, so we're probably going to end up somewhere here. So this is my point B. Now we're going to have some interesting things happening. Possibly we have negative value. So what does it mean to have negative pi over 3 angle? So if positive values, we were moving counterclockwise, so for the negative values it makes sense to move clockwise. So we're going to move, instead of this direction, we're going to be moving this direction, pi over 3 units. Pi over 3, it's roughly 60 degrees, so we're going to be facing this direction, and we're going to be moving about 2 units. So I'm going to measure about 2 units along this ray. So this is where my point C will be. And let's identify point D. Here we have something else interesting going on. So first we measure pi over 3 in a counterclockwise direction, and now along this axis we have to be moving -1. What does -1 mean? What does it mean to move along the ray -1? Well, when you facing this direction, you can think of where the arrow is pointing as a positive direction, and the opposite direction you can think to be the negative. So now -1 makes sense. So instead of moving 1 unit in the positive direction, we're just going to move 1 unit in the negative direction, and which is this way, and therefore the point D will be exactly right here. Now, if we look at point D, and ask ourselves, was this the best way to write the coordinates of point D? And the answer is maybe not. Alternatively, we could have written the coordinates of point D as what? We could have turned all the way this way. So instead of stopping at pi over 3, which is this way, we could have gone another extra half of a full rotation, and that will bring us to 4 pi over 3. And then we didn't have to deal with the negative, moving in the negative direction, because now we're facing exactly the opposite way, so we would just move 1 in a positive direction towards 4 pi over 3. So alternatively, the coordinate of point D can be expressed this way. That's interesting. Is that it? Well, turns out that that's not it. So alternatively, the second alternative is that we could have gone, instead of the opposite positive direction, we could have moved in clockwise direction, which is negative. So instead of moving pi over 3 counterclockwise, we could have moved 2 pi over 3 clockwise. And then in that case, we also would be pointing like to approach D, we would be moving in the positive direction of 2 pi over 3, exactly 1 unit. So it turns out that there is more than one way of writing coordinates of actually any point. So what we've done with point D, we can repeat that with point A, B, and C. So let's spend a little bit time discussing this behavior or a weird feature of polar coordinates. So let's take a closer look to see what happens when we look at the point -1 pi over 3 and rewrite it as alternatively as 1, 4 pi over 3, or another alternative was we wrote it as 1, -2 pi over 3. So, and it appears that these are not the only ways for us to write the coordinates of this point. So let's take a closer look at what's going on. So what's going on is that when you have a coordinate system, the polar coordinate system, and you picked a point, let's say point P, and let's say one way to express its coordinates is as we discussed previously, to measure the angle theta in a counterclockwise direction, and then move our units in what is considered now the positive direction. So one way is to express it as r, theta. Alternatively, we can actually, instead of measuring angle theta, we can actually push further and add another pi. So we can go theta plus pi. That will bring us to the other side, and what used to be positive direction will now be negative, and what used to be the negative direction will now be positive. So to get to the same point, if we move theta plus pi, we now have to move in the negative direction, but the same amount. So it's going to be -r. Alternatively, what else we could have done? Well, instead of stopping at theta plus pi, we could have actually, well, we could have moved in the negative direction too, but we could have also give it a full spin. So we shouldn't stop at theta, but move all the way around. And what would this angle be? Well, this angle will be theta plus 2 pi. And when you move this much, your positive direction now is your original positive direction, and your negative direction will be again the original negative direction. So if you give it an extra 2 pi radian spin, then you have to now make it r again. So what's the rule? Can we see the pattern here? And the pattern is actually pretty straightforward. If you have a point r theta, you can add or subtract an even number of pi. So 2 pi, 6 pi, 4 pi to theta. So that's just you adding an extra spin. And then nothing happens to r. R remains r. However, if you take an odd number of pi and add to theta, that means you're gonna you can add any number of odd pi, like 7 pi, 9 pi, so that means you're gonna end up revolving some even number and then have still an extra pi, and that extra pi will take you to the other side, and when it takes you to the other side, now you have to move in the negative direction. So when that happens, you would just have to throw a negative in front of r, and that's the rule. Instead, we formally can write it, we can express any even number as 2k, and any odd number we can express as 2k plus 1. And now we know that every point in polar coordinates can be expressed in multiple ways. So you may ask, what is which way do we prefer? And the answer, it depends. Sometimes we prefer to write our points to have radius, or the radial coordinate, to be positive. Sometimes that's the standard. Sometimes we prefer to write all our points in such a way that theta is always between 0 and pi. And sometimes we prefer to have our theta written in such a way that it always falls in this range. So it really depends on the preference. So let's take our points from the previous example and let's rewrite them to satisfy the proposed conditions. So 1 3 pi over 4, since 1 is already positive, there isn't much you can do here. Also 3 pi over 4 is in this exact interval, so we wouldn't change anything. And now to satisfy this condition, we have to do something to 3 pi over 4. And the only thing we can do is we can add and subtract even and odd number of pi's. So notice that if I subtract pi, so 3 pi over 4 minus pi will give me negative pi over 4. And when you subtract an odd number of pi's, such as in this case we subtracted 1 pi, you have to change the sign of the radial coordinate. We do the same thing here. This one is actually nice. When the point is in first quadrant, it kind of satisfies all the standards that we have proposed here, so we don't have to do anything here. Here r is positive, so we don't have to do anything. However, now since the angular coordinate is negative, in order for us to bring it into this range, we have to add pi. So negative pi over 3 plus pi is exactly 2 pi over 3. And since we added an odd number of pi's, we're going to throw the negative in front of the radial coordinate. And that actually satisfies this condition. So now here, the same thing. The condition tells us we want a radial coordinate to be positive, so let's make it positive. But when you make radial coordinate positive, that means when you're flipping the sign, that means you have to add or subtract pi or any odd number of pi's from the radial coordinate. So let's just add a pi, and then it becomes 4 pi over 3. Now it does satisfy the condition of this condition, the second condition, and finally pi over 3 also satisfies this condition as well. So we don't need to do anything here to satisfy that condition. So what do we know from this exercise is that every point can be written in more than one way. So any issues that we're gonna have with polar coordinates will be due to this fact. So in the future, if you're doing the problem and it looks like you forgot an answer, so you thought there was one answer to the problem but there are two, it's going to be because of this fact. It does create certain issues, but the benefits outweigh the issues. So we're gonna stick with polar coordinates for a while. Now the next thing that we need to address is when you have multiple coordinate systems, such as in this case we have Cartesian, now that we know Cartesian, and polar. The next question is, how do we convert from one to another? In other words, if we have a point for which the x and y coordinates are given, the question is, how do we produce the polar coordinates, and vice versa? If you have polar coordinates of a point, how do you produce the x and y coordinates? So let's start with this one, and let's talk about the conversion. So to understand the conversion, all we have to do is to superimpose the two coordinate axes, two coordinate systems, one on top of another. And we draw this diagram. And if we assume that the r and theta of this point are given, and the question is to determine the x and y. So geometrically, where is r and theta and x and y? R is this, theta is the angle, x is the length of this leg, y is the length of this leg, and it seems like we have a right triangle. So from our knowledge of trigonometry, we immediately develop the following relation. X will be equal to r cosine theta, and y will be equal to r sine theta. And that's exactly the rules that we're going to use for conversion. So for example, let's convert the point 2, pi over 4 into x, y. So let's find the Cartesian coordinates of the point 2, pi over 4. So we're just going to follow the steps that we outlined. So x will be equal 2 times cosine of pi over 4, and y will be equal to 2 times sine pi over 4, and in this case it's actually the same. So the x and y coordinates will be radical 2, radical 2. It may be surprising, but really not. But these formulas work just fine for any r and theta. Positive, negative, it all works out nicely. So that's why, that's why we're gonna like the polar coordinates, I guess. Even though there are multiple ways to write each point, there are certain things that make it easy to work with. So now let's reverse the process, and to reverse the process means we're now going to assume that we have x and y given to us, and we're going to do the conversion and find the r and theta. So the image doesn't change, right? So we're still going to have the same image once we superimpose the two coordinate systems one on top of another. And the relations won't change either, but since we're interested in another direction, we need to look for other relations. And how do we find r if x and y are given? Well, look at this right triangle, and according to Pythagorean theorem, r squared will be equal to x squared plus y squared. Also, the tangent of theta is equal to y over x. So why don't we solve these equations? And this is where we need to be careful. If you solve the first equation algebraically, you have to acknowledge that there could be two solutions, right? So r could be positive or r could be negative. And remember, in polar coordinates, r indeed can be positive or can be negative, so we cannot immediately dismiss one or another. And also in trigonometry, we learn how to solve this equation, and this equation has infinitely many solutions that in general can be expressed like this. You take the arctan of the y over x, but the solutions repeat every multiple of pi. So for different values of k, you may get a different value of theta. So now this is where we have to be careful. I'm not going to tell you how to do this, but you have to carefully make sure that your k and plus minus make sense. So I'm just going to write here match the plus minus and k. So make sure that your values that you produce make sense geometrically. So let's do a couple examples here to see how it all works out. Let's do an easy example first. So let's convert the point with Cartesian coordinates 5 and 12 into polar coordinates r and theta. So to do that, we're going to set up the following equations. As we discussed in the previous slide. So the first equation will give us simple quadratic equation, and the second one will give us a simple trigonometric equation, and solving it will give us the following answers. So r could be plus or minus square root of 169, which is 13, and theta can be arctangent of 12 over 5 plus pi k. Arctan of 12 over 5, if you can use a calculator, it will be 1.18, and since we're writing everything in all the radians in decimal form, instead of pi, I will write 3.14, and k is k. So from the first equation, we can pick a positive 13 or negative 13 root. And in the second equation, we get to choose k. So not every plus minus will work with every value of k. So to help us with the choice, let's draw a quick diagram. We have 5, 12. It's the point in the first quadrant. And by drawing it more or less accurately, you can pretty much identify what would be 1.18 radians. It's right here. So we see that if I choose 1.18 radians, which means I'm going with k equals 0, then I will be facing the first quadrant, and then I can just go with a positive sign for r. So one of the answers could be 13, 1.18 radians. Alternatively, I can choose k to be equal to 1, or I can choose my sign to be negative. And if I do that, so what happens when we choose k to be equal to 1? That means we spin an extra pi. Pi is 180 degrees, so 1.18 plus 3.14 will take us here, which will be 4.32 radians. So if you choose k equals 1, your angle will be 4.32 radians, but you'll be facing now the opposite direction from the first quadrant where you want to be, but we can still come back and land on this point if we choose r to be negative 13. So again, not every sign will work with every value of k, so you have to be carefully matching the two. So here we have identified 2 answers, but in reality there are many more. Let's do another example. Let's consider the following point. This time we will take a point in the second quadrant and we're going to find its polar coordinates. First of all, we're going to set up these equations per our earlier discussion, and the second equation will look like this. Now, solving these equations will give us 2 possible values for r, the plus and minus 5, and we also get infinitely many values for theta. So we're going to get arctan of negative 4/3 plus pi k. Using a calculator, we can compute the arctan as negative 0.93 plus pi k, but since we're using since we're writing that radians in decimal form, I'm going to write pi as 3.14, and in the first equation we get to choose between plus and minus. In the second equation we get to choose k. If we choose k to be 0, then the angle theta will be negative 0.93 radians, and which value, positive or negative, 5 will work with this choice of k. In the second quadrant, the point will be somewhere here, negative 3, 4. But if you choose k equals 0, negative 0.93 radians will be facing this way. So in order for you to still land to this point, we have to choose r to be the negative 5. So this is going to be one answer. However, if you choose k to be 1, and when you do so, you're going to end up with angle going this way. It's going to be 3.14 minus 0.93, which is same as 2.21 radians. So if you choose k to be 1, then you are facing this way, and then you should be choosing r to be positive 5. So again, just want to remind you that not every value of k will work with every choice of the sign for r. And you can try to memorize these rules, but it's always better to just understand what's going on and draw a quick diagram and figure out the answer that way. So let's consider another example. Let's go to the third quadrant and let's find the polar coordinates of this point. Just like before, we're going to set up first and then solve the equation for r and theta. And there are 2 solutions for r, plus minus square root of 100, which is plus minus 10, and there are infinitely many solutions for theta that can be expressed like this in general form, but finding the arctan of 4/3 will give us this, and then writing pi in decimal form will produce this form of the solution. At the top we get to choose plus or minus, at the bottom we get to choose k, and if we choose k to be equal 0, which is kind of default choice, so choosing theta to be 0.93 radians, should I go with plus or minus 10? A quick sketch shows us that 0.93 will be facing that direction, but the point -6, -8 is actually right here. So if I want to face this direction but land over here, I better be moving in the negative direction. So we choose -10, and therefore this is one way to represent this point. Alternatively, we could have chosen k to be 1, then would be landing on here, so it will be 0.93 plus 3.14, which is 4.07 radians, right? And if you choose k equals 1, then your radial coordinate is 4.07 radians, and in that case you can go with a positive 10 as your r value. That will take you exactly where you want to be. So we introduced the idea of polar coordinates, and we practiced performing basic tasks in polar coordinates.